Okay, today we'll continue talking about open and closed sets. So last time we talked about what an open ball and a closed ball are, and we defined an open set to be any subset of a metric space such that any point in the open set, such that any point in that set has an open ball centered at that point that's contained in that set. So if a set has that property, it's called an open set. So we have an open ball and an open set, and of course what we would like is for an open ball to be an open set, and that's in fact the case. Let's prove that. So proposition is in any metric space an open ball is an open set. Okay, so the proof, well, let's call the metric space E. An open ball is an open set. Well, what does that mean? So suppose that we have an open ball, so let P be an E and R greater than 0. So we want to show that this open ball is an open set. And what does that mean? Well, we need to show that if you take any point in that open ball, so here's, let's draw a picture. So here's P, you have a radius R, and to show that this set is open, right, this set, what do we have to do? Open means that at any point inside that set, there is an open neighborhood. So if you have a point here, say Q, right? You want to show that there is some open neighborhood centered at Q that's completely contained in that set. That's what you want to construct. So let Q be an element of this open ball. We want to show that there exists some, maybe R prime greater than 0, such that the ball of radius R prime centered at Q is completely contained inside the ball of radius R centered at P. Well, what could this R prime be? I mean, if you look at the picture, this gives you a good idea of what R prime should be. So R prime should be the radius of this small ball, and what could that be? Well, let's see. The picture suggests that so let's look at the distance between P and Q. Right. Well, from the picture, it suggests that if you take R prime to be any number that's less than R minus the distance between P and Q, then that will work. So let R prime be such that, so this positive number be such that R prime is less than the distance, it's less than R minus the distance between P and Q. First of all, let's check that this is positive. Okay. So why is R minus the distance between P and Q positive? Well, because Q is inside the ball of radius R. So by definition, the distance between P and Q is less than R. this is fine. So we just let r prime be that. Okay, now let's prove that we have this statement for this value of r prime. So we would have to let say q prime be an element of this. Then, well, what does that mean to be in this ball? It means that the distance between q prime and q is less than r prime, right? And we want to show that the distance between q prime and p is less than r. Well, we know how to connect these things. We use the triangle inequality, right? We have that the distance between q prime and p is less than or equal to the distance between q prime and q plus the distance between q and p. Okay? And the distance between q prime and p is less than r prime plus the distance between p and q, right? And r prime is less than r minus the distance between p and q. This plus the distance between p and q, and this is equal to r. So therefore, the distance between q prime and p is less than r, which proves what we want to prove. So this shows that any open ball is an open set. So this is a good proof to just be able to make sure you can do if you're taking an analysis course. This is a relatively, I think, simple proof. I mean, using the picture, it gives you a good idea of how to do it, and the proof basically follows from the definitions. It's just unpacking the definitions and exactly what you want to prove, and then using the triangle inequality here, right? Here we use the triangle inequality. So it's a fairly simple proof, but it uses some facts about the distance function. Okay, so what do we get as a result of this fact? So the open subsets of a metric space E are precisely the unions of open balls of E. Okay, why is this true? Well, so suppose that you have an open set, so let U be an open set subset of E. Then at every point, okay, so if you have an open subset, so here's U, your open subset of E, right? Then at every point P, there's some neighborhood around P that lies completely in U. So therefore, if you take every single point in U, there's going to be some neighborhood around it. So therefore, okay, so since U is the union of the elements of P, right, then, okay, at each P there is some radius R that completely, such that the ball of radius R centered at P lies completely in U, and so therefore the union of P and U of the ball of radius R, maybe with respect to P, centered at P. This union is equal to U. Okay, let's explain why. So each of these maybe I should say, to be more precise, for some r sub p greater than 0 for every p in u, right? Okay, why is this true? Because each p in u has some neighborhood that's completely contained in u. So therefore, the union over all p must also be contained in u, right? On the other hand, if you take an element in u, okay, say p, then p is obviously contained in this union. So therefore, u is equal to this union of open balls of E. Okay? And one thing to keep in mind, so some remarks, is that we proved before that when you take a finite intersection of open sets, it's open, but an arbitrary intersection of open sets need not be open. So for example, if you take in R, so here's R, so here's 0, and let's say you take a bunch of intervals of radius 1 over n, so if you take this interval from negative 1 over n to 1 over n, and then take the intersection of these for all n greater than, so n being integers that are positive, this, I claim, is just the number 0. Why? Okay, so I'm taking these intervals and they're getting smaller and smaller, and I'm just taking the intersection of all of them. Well, we know that 0 is contained in each of these intersections, so therefore it's, 0 is contained in each of these intervals, right? So therefore it's contained in the intersection of all of them. Conversely, if you're contained in the intersection of all of them, why must you be 0? Well, suppose that you were not 0, suppose that you were like not at 0, say here, okay, if you were, say, at A, which is not 0, then you can just take n large enough so that 1 over n is less than A, and then that interval will not contain A. So that explains why this intersection is just the set consisting of 0. And the set consisting of 0 is not open. Okay, because, right, by definition, because in order to be open, you have to contain around each point an open ball in it, and of course this set consisting of just 0 does not contain an open ball. And this is with respect to the standard metric in R. Okay, so that's open sets. Now it's time to talk about closed sets. So we talked about closed balls, but let's define what it means for a set to be closed. Definition is a subset of a metric space E is said to be closed if its complement well, let's call this subset S, if its complement, which is written like this, is open. And what does the word complement mean? The complement means complement means all the elements that are not in S. So these are elements in E such that X is not an element of S. Okay. So for instance in R2, you can have all the points here. This would be open, and you can have a closed set like this. This would be closed. And intuitively, the reason it's closed is because if you take an element outside it, say here, right, because that closed set contains sort of the boundary, if you take an element outside that set, you'll be able to find some epsilon or some radius such that the open ball centered at that point with that radius lies completely outside that set. So the complement is open. Okay. I should have made this small ball dotted. But anyway, yeah. Okay, so now notice that open does not mean not closed, and closed does not mean not open. So there are metric spaces where you can have sets that are both open and closed. For instance, the empty set is, one can check that the empty set is both open and closed. Well, why is that? So the empty set is closed. Well, that would mean that the metric space E is open, which we proved before. So the empty subset is both open and closed in any metric space. Right. Now before going on to those general properties, let's just check that if you have a closed ball, it is a closed set. So proposition in any metric space a closed ball is a closed set. Okay, proof. Well, so let S be the closed ball of center P naught in E and radius R. So that's our closed ball, and we want to show that the complement is open. So we should take an element P in the complement, and we want to show that there is some open ball centered at P that lies completely in the complement. Okay, let's draw a picture to get an idea of what that's going to look like. So here's P naught. Let's say this is R. Okay, so here's our set S, say. Let me just do this to make it clear that's just scratch work. And now we have a point P, right? Now what can we take for our radius around P? Well, it's gonna involve the distance between P naught and P, and it's also going to involve R. So here's the distance between P naught and P, and here is R. So what do you think we should do? Right, we should take R prime be, such that R prime is less than the distance between P distance between P naught and P minus R. By the way, why is the distance between P naught and P minus R positive? Because yes, since P is outside this. Okay, so S consists of all the points such that the distance between P naught and that point is less than or equal to R. And so if you're not an S, that means that the distance between P and P naught must be greater than R. And so therefore when you subtract R, you get something positive. Okay, so let R prime be this. So just any number that's less than this, right? Let's say here. Okay. Now let's just check. So the claim is that the ball centered at P of radius R prime is completely contained in the complement of S. Well, so now we take an arbitrary element in this set, so say Q. Right. So let Q be in the ball of radius R prime centered at P, then that means that the distance between Q and P is less than R prime, and to show that Q is not an S, right, that means that we want to show that the distance between P naught and Q is greater than R. So we have the distance between P naught and Q is less than the distance from P naught to P plus the distance between P and Q, and then this distance between P naught and P is you see, this is the wrong inequality. We want this to be greater than something. Okay, now we use the trick. This is not correct. We want to say that this is the distance between P naught and Q, right? This is because they're just equal, and then plus the distance between Q and P minus the distance between P and Q. Right, and the distance between oh, okay, by the triangle inequality, this is greater than or equal to the distance between P naught and P. Right. So you have this minus the distance between P and Q. And now, what do we have? Well, we know that the distance between P and Q is less than R prime, and so therefore minus the distance between P and Q is greater than minus R prime. And we know that the distance between P naught and P is greater than R prime plus R. Right. So this minus the distance between P and Q, but R prime minus the distance between P and Q is greater than 0. yeah, this is correct, right? It's from this, and then when you subtract the distance between P and Q, this is greater than minus R prime. Oh, yes. So therefore, this is greater than R. Right. Yes. Okay, and then that shows what we want to prove. So that's the proof that a closed ball is a closed set. Okay, and finally we'll conclude with some statements that's analogous to what we proved before about open sets. So the proposition is that for any metric space E, first of all, E is closed. Okay, well, why is E closed? So we want to show that the complement is open. Well, what's the complement of E and E? That's just the empty set. And we know that the empty set is trivially open. So that proves number one. The second one is that the empty set is also closed. We explained that before. What do we have to prove? We have to prove that the complement is open. The complement of the empty set in E is just E, and we know that E is open. So that proves number two. And then number three is the intersection of any collection of closed subsets of E is closed. And then the fourth one is the union of a finite number of closed subsets of E is closed. Okay, so let's take a look at the proof for, so 1 and 2 we've done. For number 3, so let's say that you have a collection of closed subsets of E. Okay, say intersection of alpha in A of S alpha, where S alpha is closed. Well, we know, so we want to show that the complement of this is open. Well, we know that the complement of this is equal to the union of the complements. So if each S alpha is closed, then S alpha complement is open, and this is a union of open sets, which we've proven is open. So this is open, which implies that the intersection is closed. Then the fourth one, the union of a finite number of closed subsets. So let's say that you have the union of S1 through Sn. So the complement is the intersection of the complements. So I can write it as this. So if each Si is closed, then this is open. Because we've shown that it's an intersection of the complements, and we know that each SI is closed, so therefore the complement is open. So this is just a finite intersection of open subsets, which we know is open. Okay, so that's the proof of that. We'll talk a bit more about, maybe I'll just leave it as an exercise, and then we'll come back to this next time. To show that any finite subset of a metric space is closed. That's a good exercise. And we'll come back to this, and then we'll talk about bounded sets. A short video on bounded sets. Okay, so today we continue talking about open sets. The main thing we proved was that any open ball is an open set, and that led to the conclusion that the open sets of a metric space are just the unions of open balls. And again, the idea was that at every single point in the open set, there's some open ball contained in it, so you just take the union of all those. And then we talked about closed sets, and by definition, the closed sets are precisely the complements of open sets, and we showed that a closed ball is a closed set. And then we got some simple properties about closed sets. Any intersection of closed sets is closed, but for unions you need to take a finite union of closed sets. If you take an arbitrary union, it might not be closed. Okay, that's the end of this video. Thanks.